This lesson's a bit of grade 11 review, so if you're already comfortable with grade 11 stuff, then by all means get started on the homework. Otherwise, follow along with me in this episode. Alright, first off, let's just talk about how a nuclear reactor works. In a nuclear reactor, there's uranium in there, and when the uranium goes through nuclear fission, as it breaks apart, it releases a lot of thermal energy. And with thermal energy by itself, we can't do much about it. I mean, if you go out of control with that, then yes, you have a nuclear bomb. But if you try to, regulate it and try to output the heat, how do you make that heat into some other form of energy? And it's through this crazy long process over here. All right. Well, what we do is at first we release the heat into water, and then with the water we boil it off and convert it to steam. With the steam, it creates pressure, and the pressure can be converted into circular motion through a fan. A fancy fan is called a turbine. And as it spins around and around and around, it causes a motor and a magnet to move relative to each other, and by doing that, it generates current electricity. And, that's the gist of it. Of course, if you look at this carefully, you'll see that there are three different regions of water. All right, we'll start off with the water that's heated over here. This is called a can-do reactor because, yeah, it is invented in Canada. That's where the can comes from. And D is for deuterium, which is a type of water. All right, it's water which is pretty heavy, a little bit heavier than ordinary water. So if you decide to, freeze it and make it into an ice cube, the density of that's greater than regular tap water, so it will sink to the bottom. Anyways, it's used as a moderator to regulate the rate of nuclear reaction. And another side thing it can do is that because it's water, it can transfer thermal energy around the system as well. All right, so it transfers the thermal energy into this fresh distilled water. With the deuterium water, it's kept in its own isolated system. For one thing, it's near nuclear stuff, so you don't really want to contaminate anywhere else. But number two, one of the cool things about this technology over here is that with regards to uranium, it only reacts if the neutrons bombard the uranium at a proper speed. If it goes too quickly, it'll just zip right by it, and if it goes too slowly, it'll just bounce off of it, kind of like a ball off a wall. All right, so it has to travel at the perfect speed. And the interesting thing about deuterium water is that it helps moderate it and control it to move at its proper speed. So if any time where there's a runaway reaction, all they need to do is just simply drop all of that heavy water, and the reaction stops. Anyways, the thermal energy then is then transferred into this distilled water here. You don't want to use any other form of water because, for one thing, if it contains calcium in it, it'll calcify the surface. Also, if it's not water that has a neutral pH, it'll slowly erode away at the system. So there are various reasons for it to use this distilled water. But distilled water is very expensive to manufacture, so you don't want it just to evaporate into the world. You want to recycle it again. All right, how you recycle it? Well, you need to start cooling it down. How do you cool it? Well, you hope that this is near a large body of water, and they'll just pipe the pipes underneath the basin of the lake, and that will just transfer the thermal energy over there. Of course, if there's any organisms that lives down there, well, that's an ugly looking fish. Here you go. Here's some nice looking fish. They may suffer from it because some fish only thrive at certain water temperatures. So you can imagine the environmental concerns of this. Also, warmer water tends to evaporate a lot faster as well. Oh yeah, that's what I wanted to share with you next. With regards to this one over here, the nuclear power plant found in Homer Simpson's work. What exactly is this crazy stuff over here? Well, this may give you a hint of where the Simpsons may live. All right, and which Springfield is it? Well, one thing for sure is that if you end up seeing this, that Springfield does not have a large body of water nearby so that they can go and dump the thermal heat. Instead, these are evaporator tubes where they just have the pipes going around in circles. All right, and they keep the base just naturally aspirated. Yeah, you could use fans, but it's not really necessary because the warm water will cause the air to rise. And as the warm air rises, it draws in cooler air underneath, and this is a more natural process of releasing this thermal energy. So yeah, these systems over here, they are not 100% efficient. All right, a lot of it is just dumped away as thermal energy. And that's just the reality of the game. But the benefit is that with all this abundance of thermal energy, it's rather cheap to manufacture electricity. In fact, if you just stare at your thumb right now, if you find a piece of uranium about the size of your thumb, that should be able to heat up your household for almost a year. So that's how little uranium is needed per house. Okay, so with regards to uranium, when you bombard it with a tiny little neutron, it causes it to break apart. And if you ever tried, breaking, I don't know, anything apart, like for example, ripping an orange in half or an apple in half or even Lego pieces in half, you never get it perfectly in half, right? One side will inevitably be slightly larger than the other side. So yes, that uranium can break down into either barium or krypton, or maybe break down to antimony and rubidium, or all these other examples as well. All right, so there are tons of different possibilities. So when we do our calculations, normally we do our calculation based upon just one sample uh, decomposition or nuclear fission. All right, so the laws of conservation of mass energy comes down to this formula here, or E equals mc squared. Where here in Canada, we just want to add in that little delta symbol over there because, oh, not here, over here, because we need a change in mass in order for energy to be released. And then with that, we can then perform some useful form of work afterwards because there will be a delta E. All right. So this formula also goes by a secondary name. It's also known as rest energy, and we'll explain why in tomorrow's episode. Right? But let's just get through this rest energy calculation. Right? How much energy exists inside any given atom? Well, here's the interesting thing. This formula works by the principle of knowing that the atomic mass of any given substance is different than the mass of all the different parts. So if you were to measure the mass of a proton, the mass of a neutron, and the mass of an electron, the individual components have a greater mass than your end outcome. So that difference in mass is what results in energy. All right. And well, what's that energy for? Well, in this case over here, this is known as binding energy. All right. Where it's the energy used to hold the nucleus together. It's also the same amount of energy needed to break the nucleus apart if you ever need to do that in the future. All right, and these are known constants over here. You can either measure it in kilograms or you can measure it in U, also known as AMU. What exactly is AMU? Well, you take a piece of carbon. All right, here's a lovely piece of carbon, and you break it up, and you break it up even more. In fact, you break it up into 12 pieces. So 1/12 of a carbon atom is 1 AMU. That's all it is. So we're taking carbon. Yep, we're taking that carbon. Wait, that doesn't make any sense. There you go. Yeah, you just take one slice of carbon, break it, divide it 12 different ways, and then you get the value of 1 AMU. And here is the conversion ratio. All right. So really, for all these calculations over here, we're just taking this kilogram equivalent, dividing it by this, and then that will give us these decimal numbers. Another interesting thing to note is that when you take a look at the mass of a neutron, it's not exactly the same as a proton. It actually has a greater mass, just by a smidge. All right. So once again, when we describe about the amount of energy that is emitted in any sort of nuclear reaction, we're looking at the fluctuations in its mass. So this formula here is not an official formula, but it's one just to keep in mind that the mass defect, or the change in mass, is the difference in mass between what you had before versus what you have afterwards. All right, and let's go through this calculation. Let's say that you have uranium, isotope number 235, and it breaks down into barium and krypton. How much nuclear energy is released from one atom of uranium? First, we need to find out the mass defect. So we're going to subtract the mass of the uranium itself and the mass of the neutron at the beginning. And again, we can't just use 235 and we can't just use 1 for the neutron. We need to carry as many significant digits as possible in our calculations because we're looking for these tiny minuscule differences in mass. After all, if you just rounded this off to the nearest whole number, then you'll get to an answer of 0, right? 235 plus 1 will give you 236, and 141 plus 92 plus 3 times 1 will also get you 236. So if you round to the nearest whole, well, then you're not going to get any sort of mass defect. So please carry as many significant figures as possible, or decimal places in this case over here. Also, another common mistake is that students forget to multiply the neutrons by the quantity that are emitted after the chain reaction. All right, and here you go. Here's the mass defect. In general, the mass defect usually has a value that's less than 1, although every now and then it is possible to get numbers that encroach 1 and above. Anyways, now that we have the mass defect, now we can sub into this formula. Maybe not directly yet because this is still measured in AMU. So we need to multiply this by that conversion ratio, which I don't remember off the top of my head. This number over here. Okay, we need to multiply by that to convert it into kilograms. Yeah, right over here. Okay, and then now you can sub this value into your delta M, multiply by the speed of light, don't forget to square it, and you get your answer measured in joules. Now you'll notice that this measurement in joules, it's a very small number, all right? So we don't use that as our scale. For example, if you're an American, if you're measuring long distances, you'll measure it in miles. If you're measuring shorter distances, like for example in a football game, you'll probably measure it in yards. And if it's even shorter, you'll measure it in feet. And for smaller measurements, you may measure it in inches. And there's a fraction of an inch. I forgot what the term was, but you may measure it in fractions of an inch as well. All right. And you know, these numbers are all really weird numbers, like 5860, I think. Don't quote me on that. 5860 feet in a mile. There are 3 feet in a yard, that I know. A foot is, well, the definition 1 foot. And an inch is 1/12 of a foot. All right. Oh, mils. That's what I was thinking of. Mils, which is, I think, 1/1000th of a millimeter. So then you'll have that of a foot. All right. And yeah, you'll choose the unit scale for whether if you're dealing with large measurements and small measurements. And you can see these conversion ratios, they're all nasty. All right. And you know what? In the world of energy, it's just as weird as well. All right. Where if you need to measure very large quantities of energy, that's why your house measures it in kilowatt hours. So 1 kilowatt hour. What does that translate into? It translates into roughly 3.6 million joules or 3.6 megajoules. All right, so if you ever need to measure large quantities of energy, you'll measure it in kilowatt hours. For smaller units, like the base reference unit, then yeah, you have your 1 joule, which is also equal to 1 joule. All right, but if you need fractions of it, for example, 1.602 times 10 to the negative 19 joules, then that's the equivalent of 1 electron volt. All right, so it's a very small quantity of energy. And if that's too small, then yeah, you can upgrade it to 1 million electron volts. So you do negative 19 plus another 6, you get 1.602 times 10 to the negative 13 joules. So yeah, you can convert joules into mega electron volts by using this conversion ratio right here to solve for that, if you wanted to. There is another shortcut as well, where, oh, is it 931.5? I think that's a conversion ratio. 931.5. It's a number that you use for MeV over C. Is it? No, MeV over U, which is equal to 1C squared. In other words, if you want to find out your 174 very quickly without going through all these other calculations, then you'll start off with your 0.18667 U's. So you have, was it E equals MC squared, which is equal to 0.18667 U. And you know you're going to go through the effort of multiplying by this number, multiplying by this number squared, and then dividing it by, dividing it by 1.602 times 10 to the negative 13 over and over again. So instead of spending all that time doing it over and over again, just multiply that by 931.5 MeV over U, and that'll quickly get you to your answer of 174 MeV. So that's a much faster way of getting to your final answer. All right, and I think that's it for today. Best of luck in tonight's homework.